Under the subject of geology, we study the earth. The term earth science is a further enlargement of the perspectives covered under geology and is defined as the science dealing with all aspects of earth in which we live. A thorough understanding of the earth's processes and their ramifications have great relevance to the societal development and the progress of the nation. In UGC model curriculum, structural geology is prescribed as one of the fundamental paper of earth science. Structural geology is a subfield within geology which focuses on the study of geological structures with the goal of learning how, when, and why they form. A structural geologist identifies geological phenomena looking specifically for signs of deformation which show the kinds of stress put on the rock as it forms. Deformation can reveal the angles of stress, the origins of the stress, and its intensity. How things form and change over time, a specialist in structural geology can draw a number of conclusions which may be used to gain a deeper understanding of geology. Primary data sets for structural geology are collected in the field. Structural geologists measure a variety of planar features, that is, bedding planes, foliation planes, fold axial planes, fault planes, and joints. Both petroleum geology and mining geology, folded and faulted rock strata commonly form traps for the accumulation and concentration of fluids such as petroleum and natural gas. First paper of UGC model curriculum has covered the introductory part of structural geology, and sixth paper of the curriculum is fully based on the topics of structural geology.
Before we go into the detailed discussion on structural analysis of the data measured in an area, let us understand very clearly about the difference between the stereographic projection and the other method of azimuthal projection called the equal area projection. In stereographic projection, as we have discussed, the circles of same size are plotted as circles on the stereographic projection, but of different sizes. Areas measuring the same angular measurement close to the center are of smaller area, smaller size, while same size areas close to the periphery occupy a larger size. In case of equal area projections, however, the things are different. The basic principles of stereographic projection and equal area projection and the differences between the two can be obtained from Ragan's book on geometrical techniques that was first published in 1985. The basic differences in appearance of equal area projection from stereographic projection is that the circles of identical size in case of an equal area projection will appear as ellipses of various shapes in different parts of the projection with different lengths of major and minor axis, but all will be of equal area. Similarly, the angular areas with identical angular distances plotted on an equal area projection will be of identical area, but of different shapes when plotted towards the center or towards the periphery. Before we go into the discussion of structural analysis itself, let us have an idea about the stereographic net and its preparation. This is how a stereographic net or equal angle net or wolf net looks like, and this shows the development of the stereographic net or stereographic grid. This shows how planes of identical strike, but of differing true depths in opposite directions are plotted three-dimensionally, and how their stereographic projections are obtained on the median or equatorial plane of stereographic projection. The equal area net or SMID net, on the other hand, looks slightly different from the equal angle or wolf net. It has an appearance like this. Methods of structural analysis. But before we go into the methods of structural analysis, let us first understand very clearly why we need to do structural analysis of an area at all. We must understand that the purpose of studying structural geology or the structure of a terrain of an area is to understand the evolutionary history, the structural evolution of the rocks in the area through time. Multiple phases of deformation might have affected the rocks in an area. We need to unveil the tectonic evolution, how the different deformation phases affected the rocks and how the terrain evolved, how the tectonics of the terrain evolved through geological time. For this, it is essential to understand first the orientation of the structural parameters related to each phase of deformation, and also how the later phases have affected the earlier structures. For conducting the structural analysis over a large area, it is essential to do a series of things. For a structural geologist, first thing that is necessary is to prepare a geological map of the area. While preparing the geological map of drawing the lithocontacts on the map, it is also essential to measure all possible orientations of all planar and linear structural elements that have developed or have been deformed during the deformational phases. Multiple planar and linear structures may form during the different phases of deformation. Separating them out into the different phases, understanding their order of development and allocating the direction of applied compressive stress to each of them is essential for understanding the tectonic history of an area. To understand the complete history, it is essential to represent all possible structural measurements on paper. Nowadays, several computer programs have been developed to plot all the data, but before we plot the data using a computer program or analyze the plotted data, it is essential to understand the basic principles of structural analysis. Let us think about an area where there have been little or practically no deformation. We must remember that even if the rocks are not deformed, in nature no ideal planar or linear structures can form. Even if a bedding plane in a sedimentary layer is for all practical purposes planar, it would show small variations in orientation, both its strike, true dip amount and direction from one point of measurement to the other. When such a planar or homoclinal body of rock, data measured on such a homoclinal body of rock is plotted in the stereographic projection, it is customary to plot only the poles. For a homoclinal sequence, the poles will be plotted as a cluster of points, if not at a single point. The average or maximum of these small scatter will give us the mean orientation of the bedding plane in the area. When the bedding planes are folded, the strike, true dip amount and direction of the plane which is being folded will show a systematic variation across the fold. On the limbs and the hinge, the orientation of the bedding plane will differ. Naturally, when we plot the poles of such a fold, if the fold is cylindrical, the poles will be plotted along a great circle. A best fit great circle can be drawn through all the variable poles of the bedding planes, and the pole of this great circle will give us the orientation of the hinge line or fold axis of the fold. This is when a single deformation has affected the rocks of an area. When multiple deformations have affected the rocks of an area, subsequent deformations further modify the original fold parameters like their hinge line, their axial plane, etc. Thus, it is necessary to analyze all the different structural elements related to the different fold phases, to separate them out and to understand the time sequence of their development. It is necessary to understand the structural evolution of an area to subdivide an area of multiple deformed rocks into homogeneous areas. For example, we might find an area in which one particular planar or linear structural element, the hinge line of the fold for example, has a more or less constant orientation. So, in another area there may be a consistence of another phase of minor structure or lineation. What we generally do is subdivide the larger area into smaller areas called sectors or sub areas, which are more or less homogeneous with respect to one particular set of lineation, either the major fold axis or the line of intersection of the axial plane and the bedding plane, and so on. The major fold axis of different phases are generally referred to as F1, F2, F3, etc. So, over the fold axis we will be discussing how the orientation of other minor structures may vary. Now, let us go back a little to the mechanism of fold formation. If there was an original lineation on a planar surface and the planar surface is folded by layer parallel compression or flexure slip, the orientation of the pre-existing line will change in different parts of the fold. It will so change that its angle with the fold axis will remain the same all across the fold hinge, from one limb across the hinge to the other limb. Thus, if we plot the orientation of the folded plane at different parts of the fold, on the stereographic projection on the great circles, the earlier lineation, the pre-existing lineation will have a constant angle with the hinge line. Thus, analysis of the geological structures, the plotting of the data, the earlier data and the later data helps us in understanding the mechanism of folding in a folded terrain. We must also remember that maybe during some deformation phases no major deformation is produced, but only minor structures like minor folds, pucker axis or small scale crenulation cleavages. The minor folds superimposed on an earlier major fold, the axis of the minor folds superimposed on a pre-existing major fold will also show a great circle distribution. However, the difference between an early minor fold deformed by passive shear folding and a later minor fold axis superimposed on an earlier major fold will be the difference in orientation of the axial planes. The orientation of the minor fold axial planes will be constant. They will have their poles plotting at a cluster or showing a maximum, while in case of a pre-existing minor fold deformed by a later major fold, the axial planes will also become folded. This is how we differentiate between folds of different generation, but of different scale. The analysis of geological structures also has to take into account the large number of structural data that are measured. We have repeatedly mentioned this. To understand the distribution of the structural data that have been measured, it is sometimes necessary not only to plot all the data, but to draw contours showing the distribution of data across the projection, be it stereographic projection or equal area projection. However, the contouring or distribution of data can only be done when it is plotted on an equal area projection. Contouring of data is nothing but counting the data and drawing lines that join points of same concentration of data, so that the maximum concentration of points can be easily or visually emphasized. Contouring or the counting of points and drawing lines joining points of same concentration are generally drawn following any of the many methods. There is the Schmid method of counting, there is the Melis method of counting, there is the Karlsbeck method of counting, and there is the Kamb method of counting. We use a contouring net or counting net over the equal area plot of points on a transparent paper or overlay and mark out the center of the area with the total number of points there. Now, depending on the total number of points plotted in an overlay, we decide at what interval contours are to be drawn, and accordingly join the points where points of same count are found on the stereographic projection, thus giving us a clearer idea about the distribution of point counts and helping us in fitting a great circle where necessary to find out the broad distribution of the data. To understand the usefulness of contouring, let us take this example. In this example, you are being shown an undeformed horizontal bed, a slightly deformed bed producing a gentle fold in it, and further deformation has caused a reduction of the interlimb angle from left to right. In the undeformed bed, which is nearly horizontal, the data, all the measurements are plotted close to the center, since the pole is vertical with a very small scatter. In case of the gentle fold, you can see that the distribution of the poles to the bedding are slightly towards the two sides, east and west, while in case of the lower interlimb angle folds, where the deformation is more advanced, the distribution of the poles to the bedding have been spread out, have been drawn out to the sides much more. Thus, the contouring of the data can help us in understanding not only about the orientation of the fold or the deformation structure, but the nature, geometry of the fold as well. Let us take an example of how analysis of geological structures are helped by plotting of different parameters, different planar and structural parameters. While discussing the geometry of folds, we have discussed how folds may be non-cylindrical in nature. In folds which show culmination and depression, but the axial plane remains planar. In different segments, the fold axis will have variable orientations, but all of them will be plotted on the same axial plane. Thus, a plain non-cylindrical fold showing culminations and depressions, if their data are plotted in a diagram known as a synoptic diagram, on which more than one structural feature is plotted, there the axial plane will be plotted as a great circle, and on it the fold axis measured in different subareas or sectors will be plotted at different points. Structural analysis by plotting the minor planar and linear structures on stereographic or equal area projections also helps us in understanding about the type of deformation the rock has undergone. While discussing foliations and lineations, we have seen how tectonites or deformed rocks may be either S tectonites, where the planar deformational structure is dominant without any notable linear structure. They may be L tectonites, where a linear diastrophic structure is dominant without the development of a planar structure, and there may be LS tectonites, where both foliation and lineation have resulted from the deformation. If we consider the concept of rock deformation, the strain ellipsoids, with this we can see how a S tectonite represents a flattening type of strain or more like oblate strain ellipsoids, how a L tectonite represents a constrictional type or prolate strain ellipsoid, and an LS tectonite represents a more general type of strain where both flattening and constriction has taken place. The plotting of data, the distribution of the foliations and lineations on azimuthal projections like stereographic or equal area projections helps us in identifying the deformational history, the strain pattern within the rock.